What's up, guys? It's Mr. Meehan. Today we're going over Unit 2, Lesson 2. This talks about proving that two lines cut by a transversal are parallel using the converses of parallel line-angle relationship theorems. And then it says we're also going to use properties of parallel lines and transversals to solve real-world problems. So let's do it. This first problem says Mr. Mark analyzes the diagram to see if line L is parallel to line M. Alright? Mr. Mark states that the lines are parallel because of the alternate interior angles theorem. So what he is seeing is that angle 2 and angle 3 are alternate interior angles, and that since it says those angles are congruent, then L and M must be parallel, because the alternate interior angles theorem says if L and M are parallel, then 2 and 3 must be congruent. So that's how he's coming to that conclusion. Okay? So by his logic, yes, those lines have to be parallel. Since 2 and 3 are alternate interior angles, since they are congruent, then L and M must be parallel. Alright? Part 2 here says, if the lines are parallel by alternate interior angles theorem, is there any other theorem that we could also use to say the lines are parallel? Well, what other angles are congruent? Angle 1 and angle 4. And what kind of angles are 1 and 4? They're corresponding angles, alright? So we have two congruent corresponding angles. And by the corresponding angles theorem, the corresponding angles theorem says if we have two parallel lines, then corresponding angles are congruent. So this is kind of the opposite of that. So if we have two congruent corresponding angles, then L and M would have to be parallel by the logic of the corresponding angles theorem. So let's say the other way these could be congruent is because of the corresponding angles theorem. Or if lines are parallel by the alternate interior angles theorem, is there any other theorems we can use? Yeah, corresponding angles theorem. Corresponding angles theorem. But the corresponding angles theorem and the alternate interior angles both say if we have two parallel lines, then the corresponding angles or the alternate interior angles are congruent. And right now we're kind of using the logic backwards. We're saying if we have two corresponding angles or if we have two alternate interior angles that are congruent, then the lines are parallel. So we have to have a theorem that says those things backwards, just like how we were saying it just now. So that's what we have here. We have the converse of the corresponding angles theorem. So if we say the corresponding angles theorem says if we have two parallel lines cut by a transversal, then the corresponding angles are congruent, then the converse of that would say if two lines in a transversal form corresponding angles that are congruent, then the lines are parallel. So here, if angle 1 is congruent to angle 2, then L is parallel to M. So if we have two congruent angles, then L and M would be parallel. Okay? So let's look at this example. It says, if two sailboats are sailing to the east at 45 degrees to the wind, will their paths ever cross? Alright, so here's two sailboats, and then here's a aerial view of them. Okay, same sailboats, crazy enough. It says they're traveling at 45 degrees to the wind east, and you can see that 45 degrees here, those are corresponding angles, and they have to be congruent since they're both 45 degrees. Since they're both congruent corresponding angles, we can use the converse of corresponding angles to say that their paths are parallel, right? They have to be parallel since they have congruent corresponding angles. So by the converse of corresponding angles, these boats will never cross paths because they are going in parallel directions, or parallel paths, okay? Similarly to the converse of corresponding angles, we have the converse of alternate interior angles. It says if two lines in a transversal form, alternate interior angles that are congruent, then the lines are parallel. So this is very similar to the converse of corresponding angles, except now we have two congruent alternate interior angles, and if we have two congruent alternate interior angles, then L and M have to be parallel. Okay, it's used in the same way. Let's try to prove the converse of alternate interior angles theorem. Remember, when we're trying to prove something, we can use everything we know up until this point, but if we're proving the converse of alternate interior angles theorem, we cannot use the converse of alternate interior angles theorem in our proof, okay? So step 1 would be to write the given, so let's write it out. Step 1, angle 1 is congruent to angle 2. That's given. And I always like to write it in on the diagram so it's very clear. The next thing we can say is we can say, hey look, angle 1 and angle 3 are vertical angles. So let's say, step 2, angle 1 is congruent to angle 3 because of the vertical angle theorem, VAT, right? That makes sense. Then if you follow the logic here, we have angle 1 is congruent to angle 2, angle 1 is congruent to angle 3. So step 3, we can say angle 2 is congruent to angle 3 because of the substitution property of congruence. Substitution. And if angle 2 is congruent to angle 3, and you notice that angle 2 and 3 are corresponding angles, then we can say in step 4, final step, L is parallel to M because of the converse of corresponding angles theorem. Could call it the CACAT, maybe. All right, converse of corresponding angles theorem. That's the entire proof. Now, just like we have the converse of corresponding angles theorem and the converse of alternate interior angles theorem, we also have the converse of same side interior angles theorem. So originally, the same side interior angles theorem says if we have two lines that are cut by transversal, then same side interior angles form supplementary angles. So now the converse of that would be the converse of the same side interior angles theorem, which says if two lines in a transversal form same side interior angles, same side interior angles that are supplementary, then the lines are parallel. So here it's saying angle 1 and angle 2 are supplementary. I'm going to kind of draw it like that. There's no awesome way to draw it. Let's see. Alright, you can kind of tell. I have two arcs at angle 1 and one arc at angle 2. So if angle 1 and angle 2, if the measures of those add up to 180 degrees, then L is parallel to M, okay? We're going to use it very similarly to the converse of corresponding angles and the converse of alternate interior angles. Alright, so let's prove the converse of the same side interior angles theorem, just like we did with the converse of the alternate interior angles theorem. Here, it is given to us that the measure of angle 1 plus the measure of angle 2 equals 180 degrees. So you could say that those angles are supplementary, right? That is given. So I'm going to say like kind of angle 2 and angle 1 are supplementary, kind of like that. What can we say next? Well, we can say step 2. If you look at angle 1 and angle 3, angle 1 and angle 3 form a linear pair, right? They form a straight line, which means they also add up to 180 degrees. So you can say the measure of angle 1 plus the measure of angle 3 equals 180 degrees. And that can be because of the linear pair theorem. Or some people might say like definition of supplementary. Whatever you're using would work, all right? So since angle 1 and angle 3 add up to 180 degrees, that's done by the linear pair theorem or the definition of supplementary. What we can do here is notice that in step 1, we have angle 1 plus angle 2 equals 180. And in step 2, we have angle 1 plus, let's say, I need another color, angle 3 equals 180. So since both of those statements add up to 180 degrees, we can say step 3, those two things are equal to each other. So angle 1, the measure of angle 1, plus the measure of angle 2 equals the measure of angle 1 plus the measure of angle 3. And I'll write in my colors as well. I'll say angle 1, angle 3, angle 2, angle 1. I think the colors make it a lot easier to look at. And that is because of substitution property of equality. Substitution. All right? Then from there you can subtract the measure of angle 1 on each side. So step 4, if we subtracted the measure of angle 1 on each side we would get the measure of angle 2 equals the measure of angle 3. And that is subtraction property of equality. Subtraction property of equality. And if the measure of angle 2 equals the measure of angle 3, I'll write in my colors again. Step 5, angle 2 is congruent to angle 3. That's because the definition of congruence, or definition of congruent angles, of congruence, alright, which says if two measures are equal, then the angles are congruent. And if angle 2 is congruent to angle 3, look at this. Angle 2 and angle 3 are corresponding angles. They're congruent corresponding angles. So you can use the alternate, not the alternate, you can use the converse of corresponding angles to say L is parallel to M. Converse of corresponding angles theorem, the CACAT. That's the entire proof. Last one that we're going to talk about is the converse of alternate exterior angles theorem. This is exactly like it sounds. If two lines in a transversal form alternate exterior angles that are congruent, then the lines are parallel. Okay? So here it says if angle 1 and angle 2 are congruent, then angle 1 and angle 2 are alternate and exterior angles, then L must be parallel to M. Alright? So let's prove this. Step 1, always write the given. Angle 1 is congruent to angle 2. That is given. Step 2, let's see what we can do. So we know angle 1 is congruent to angle 2. Do you guys see anything else that could be congruent to angle 1? Because I see that angle 1 and angle 3 could be congruent because of vertical angle theorem, right? Those are vertical angles, so they must be congruent. And kind of, again, if we use our colors here, it's really easy to see what's going on. If yellow is congruent to green and yellow is congruent to orange, we can say green is congruent to orange. So 2 is congruent to 3. So let's say step 3. Angle 2 is congruent to angle 3 because of the substitution property of congruence. So angle 3, substitution. Alright? Oh look, angle 2 and angle 3, those are congruent corresponding angles. So if we have congruent corresponding angles, then we can say those lines are parallel by the converse of corresponding angles theorem. So step 4, L is parallel to M because of the converse of corresponding angles theorem. Okay, next example. It says one way to build stairs is to attach triangular blocks to an angled support as shown. If the support makes a 32-degree angle with the floor, what must the measure of angle 1 be? So the step will be parallel to the floor. The sides of the angled support are parallel. Okay, so here you can see we have two parallel lines, and I'm going to kind of highlight them if you use a different color, maybe color green. All right, so those two lines are parallel lines. We can tell because it has those arrows on them right here. So those are parallel lines. If those are parallel lines, you can see that 32 degrees and angle 2, those two angles are corresponding angles. All right, so they must be congruent. So if angle 2 and whatever this angle is are congruent, then the measure of angle 2 has to equal 32 degrees. All right, super easy. The next step here would be to look at a set of different parallel lines. Let's say we have now this parallel line where that this step is right there where I highlighted, and then the floor is the other parallel line. Okay, so here we have angle 1 and angle 2. That's what I'm looking at now. We know angle 2 is 32 degrees. If you're looking at angle 1 and angle 2, you can see that they're alternate interior angles, right? They're on the interior of the two parallel lines, and they're on alternate sides. Okay, so if they're alternate interior angles, then they must be congruent. Okay, so the measure of angle 1 has to also equal 32 degrees. So what must be the measure of angle 1? 32 degrees. Here's another one. It says given L is parallel to M, L is parallel to N, my bad, and M is parallel to N, prove L is parallel to M. So it's telling us L and N are parallel, and it's also telling us that M and N are parallel. Alright? Well, if L and N are parallel, we can say that angle 1 is congruent to angle 3 because of corresponding angles theorem. Angle 1 is congruent to angle 3. That is corresponding angles theorem, the CAT maybe you could call it. Okay? And if M is parallel to N, you can also say angle 2 is congruent to angle 1. And I'm just going to include that in the same step since it's also corresponding angles theorem. Angle 2 is congruent to angle 1. Alright? I'm going to bust out my colors here. We have angle 1 is congruent to angle 3. Angle 1 is congruent to angle 2 here. If angle 1 is congruent to angle 3 and angle 2, we can say in step 3, angle 2 is congruent to angle 3 because of the substitution property of congruence. Substitution. Alright? Angle 2 is congruent to angle 3. Now you can pretty easily see angle 2 and angle 3 are corresponding angles that are congruent. So we can say by the converse of corresponding angles theorem, M or L is going to be parallel to M. Alright, so let's say it. Step 4, L is parallel to M because of the converse of corresponding angles theorem, the CAT. Alright, theorem, another theorem. It says if two lines are parallel to the same line, then they are parallel to each other. So we can say if A is parallel to C and C is parallel to B, then A is parallel to B. Alright? If A is parallel to C and C is parallel to B, then A is parallel to B. That's what we just proved up here. If L is congruent to N and M is congruent to N, then L is congruent to M. Alright? That's all that says. All this says is if A is parallel to C and B is parallel to C, then A is parallel to B. It's kind of like a transitive property through like parallel lines, right? Last couple things we're going to talk about. This example right here, it says L is parallel to N. Sorry, L is perpendicular to N, and M is perpendicular to N. Let's write it down. L is perpendicular to N, and M is perpendicular to N. That's given. What does perpendicular mean? It means angle 1 and angle 2 are going to be right angles. That's what that means. We can say in step 2, the measure of angle 1 equals 90 degrees, and the measure of angle 2 equals 90 degrees. That's just the definition of perpendicular. Like being perpendicular means to make a 90-degree angle. So let's just write down the definition of perpendicular for that justification. Definition of perpendicular. Alright? And if the measure of angle 1 equals 90 degrees and the measure of angle 2 equals 90 degrees, oh, look at this. You can say the measure of angle 1 equals the measure of angle 2. And that's just the substitution property of equality. Substitution. Right? Substitution property of equality. One of the second to last step here, if we have two measures of angles are equal to each other, we can say in step 4, the angles are just congruent themselves. So if the measure of angle 1 is equal to the measure of angle 2, then angle 1 is congruent to angle 2. That's because of the definition of congruent angles, or the definition of congruence. And then the last step, you can see angle 1 and angle 2 are corresponding angles. They're congruent corresponding angles now. So we can say, step 5, L is parallel to M because of converse of corresponding angles theorem. Boom. So what we just proved is this theorem right here. It says if two lines are perpendicular to the same line, then they are parallel to each other. So if A is perpendicular to C and B is perpendicular to C, then A is parallel to C. That's what we just proved.